Hi, my name is Eric, and this is a tutorial of electrophysiology in a 2D sheet of cardiac tissue. So the first thing we're going to do is load this model from the Continuity's public repository. So go to File, Library, Search, and we'll search for Sheet 2304. And just to verify, you can look at the model ID number 1379 and make sure you select that model. So right click and select load, and that will load the model into Continuity. So let's look at the mesh edit nodes form, and obviously here are defined the coordinates of the nodes of our mesh, but we can also look at things like the fiber angles and also the field vector tab, which contains these field variables. And these are initialized by selecting a basis number. And so you notice the field variables 1 and 2 are initialized. And we'll talk about what these things mean in just a moment. But if you look at node number 1176, you'll notice that field variable 2 has a different value for that node than for any of the others. And this is a method whereby you can define parameters that are different according to their spatial location. So let's go ahead and calculate the mesh, and then let's render the elements. We'll render the lines first. You can zoom in and out to see things a little better, and then let's render the surfaces as well. So let's take a look a little more in a little more detail at some of the components of our model. So let's look at the ionic model first. This is using the Beeler-Reuter ionic model, and we can look at some of the equations and parameters that are set in this model, such as some of the gating equations for the sodium current, for example. This also includes the Nernst potential for the sodium channels, as well as conductivities in the open and closed states, and similarly for the calcium and potassium currents. There are equations that define all of these things in here. We can also look at the voltage equation, and the membrane capacitance is also defined here. Lastly, there are stimulus parameters. And this is kind of where you can set a value for all of the nodes in your mesh, or as I said earlier, you can use a field variable, and here the stimulus magnitude is using field variable 2, which is the one that was different for that one node 1176. Now let's look at the conductivity model, and here is the conductivity tensor, and we can see that right now the conductivity tensor is isotropic, which means it's the same in all three directions, and that can easily be changed, and we can see how that will affect our solution. So let's initialize our problem by going to electrophysiology, solve, initialize. And let's make sure to send the data to the server. And finally do electrophysiology, solve, integration. And let's solve this for a duration of 400 milliseconds and leave everything else in the default settings, and click OK. Now you can watch the solution in a Python shell, which I have opened by default when I open Continuity, but if you don't have that already, then you can open the Python shell by clicking this Python idle shell button up in the corner. And it looks like I closed that, so I'll just reopen it again by clicking that same button. So this solution takes a while, so I'm going to skip ahead here. So now our solution is complete, and you can see the duration that it took. And let's render the solution by going to electrophysiology, render solution. I'll select a minimum value for a color scale of minus 80 millivolts and a maximum value of 10, and then click OK. And again, you can watch as this solution is rendered by opening the Python shell, and you'll notice that by default continuity loops over the rendering up to the point where the solution is already rendered. So you'll want to wait until the full solution is rendered to make sure you get the full thing. So I'm going to skip ahead again, and now we have the full solution rendered. And you can see that that point stimulus in the center of the 2D sheet expands in all three directions equally. A useful feature of continuity is that these models can be run from a script. So let's go ahead and reset the current model by going to File, Library, Search again. And we'll just search for the same model. And again, you just right click and select Load. And there will be a few options here. We're going to choose the second option, which is Reset Without Save and Proceed. So this resets continuity and loads the model, so we're back to our starting point. And then we'll go to File, Scripts, Script Manager. You'll see two simulations here. The first is the one we just ran with isotropic conductivity, and the second one, I'm going to select it and click Execute Selected. And this one has anisotropic conductivity, and when we click that Execute Selected button, it goes through the entire process that we just went over, including calculating the mesh, rendering the mesh, and then it starts solving. So again, I'm going to skip ahead, and it'll actually automatically render the solution. So if you just wait a certain amount of time, then the solution should be rendered on its own. So there it is, and you see that there's a difference in the conductivity of the tissue, that the action potential spreads more quickly along this 45-degree direction than across it.